yazildi.
For physiological measure of trust. For example, a touch used EEG and electroencephalography and governance response (GSR) and electroencephalography and governance response (GSR) to measure human trust towards machines. Toiletry also demonstrated that presence increases trust in the VR task. However, they only use a public measure for this resistance. Yeah. Looking towards the correlation in trust episode, Kawaki suggested that governance response is a useful tool to measure the interpersonal trust for both low and high cognitive tasks. However, he used a desktop text chat environment, and it's also between humans, basically, it's not with machines. Gupta explored the correlation between physical signals of trust and cognitive load in VR, and did find that the average correlates with a voice assistant depending on the cognitive load conditions. However, they did find that the task that they used was firstly a combination of a and-back task. This was a well-known physiological test. It's a well-known test towards measuring cognitive load, as well as a shape-selected task in virtual environment. So they just combined these two tasks together separately, and they found that the task wasn't as hard as it's supposed to be. So this is some of the little work that I like to stress upon. There's a lot more that we explored in our work actually. They are available in the paper, but for now I'm just going to summarize this in this table right here. Where our method differs is that we developed a VR environment which integrates this and-back task into a shape-selected task. So our previous work was separated. Here in this case we combine it, and we try to induce three kinds of key cognitive loads to understand its trust towards a voice assistant that will be guiding you in the task. So through our research, we will be presenting a custom VR environment meant to maximize or minimize cognitive load of our unreliable virtual agent. So we will have two independent variables here. We explore the relationship between the agent trust and induced cognitive load based on gathered physiological signals, behavioral aspects, as well as subjective feedback. So three key results. Three main results in terms of the physiological, behavioral, and subjective. And finally, we found that the EEG alpha channel and the frequency domain mean power, peak frequency for galvanic signal response, as well as total power spectral density, specifically 0.05 Hz as well as 0.12 Hz, the rounds computed per second, as well as the subjective questionnaires that we employed to be indicative of the user's trust in different cognitive states. So I'll now move on to the system design. So for our system, we use the OpenBCI EEG tab with 16 electrodes. We also use the OpenBCI GUI to stream the data out. We use the shimmer sensor for the GSR as well as heart rate variability signals mounted on the user's left hand. Maybe I could enable my laser pointer over here. So this is the GSR sensor. And we use a Java application to stream the shimmer sensor towards the Unity 3D game environment, which we developed for the shape sector task. Everything using a first-generation HTTP HMD for the participants to view the environment. So this was modified from our previous work, which was published in JRST 2019. So in this task, we separate between a primary and a secondary task. For the primary task is the shapes selected task, where the user is supposed to look for a target object around them. So it's always placed all around them with different shapes and different colors. So their target object can be seen. Target object can be seen in this yellow background. Pink background over here. So if they are meant to look for a blue cube, for example, they have to look around, and once they find a blue cube, they just select it. But all this while, the secondary task plays in the background. So while they're selecting for, they have a ladder at the top here that keeps flashing every few seconds. So this is the end-back task actually. So for end-back task, it's about memorization. So when a letter appears here, for example, B, then later on it will ask you what was the letter that just appeared, like B, for example. But that's for one back task. With two back tasks, then you need to memorize two letters before. So while selecting the shape selector, the user must also keep an eye to appearing at the same time. So by designing a task like this, it induces all kinds of cognitive loads, namely memorization for the end back, multitasking, where they have to skip between the primary and the secondary task, as well as temporal load, because between the high and low cognitive load, you use either 10 seconds or 5 seconds to complete the task. So they're only given a short amount. They're only given a short amount of time. So it's not all that hard, because we have a voice assistant to actually help the user to select an object for their primary task. So since they need to look around the environment to select for the object, there's a voice assistant telling them to either look left or right. So it always updates depending on where the user is currently facing. For the low cognitive load, for the low accuracy of the voice assistant, we set it to 50% accurate, so it's pretty much random. It doesn't lean towards accurate or not accurate. Whereas for high accuracy, it will be 100% correct, basically. If the object is to the left, it will be at the left. With 50%, so it could be lying. It's basically random. Once again, for the devices, we use the OpenBCI EEG cap with the Titan Daisy chain module, which samples up to 125 Hz, 16 channels. We place electrodes at the prefrontal, parietal, and occipital lobe of the user. As for the Suen sensor for measuring GSR and HRV, so governing skin response and heart rate variability, is sampled at 128 Hz, and all is streamed into a unique environment displayed through the HD5 VR muzzle display for the VR environment, and to also enable interactions. So as we can see in this image of here, it's enabled by laser 21.4. So you can see that we try to minimize motion artifacts. Actually, we had to strap the left hand, which is the left hand of the user, which has the GSR set back resting on their shoulder actually. And whereas we have the entire cable of the HTC5 wire upwards, so there was no pulling towards the HMD while they was wearing displacement in the EEG. So now I'll move on to the user study. A within subject user study on 24 participants, where 50% of them are female, age mean 28, and a standard deviation of 3.1. So it's a 3x2 study with two levels of accuracy actually, but we have a no voice assistant, we have low accuracy voice assistant, as well as high accuracy assistant, as well as high accuracy voice assistant. And as for cognitive load, that's low and high cognitive load. So the no voice assistant is more like for baseline. In terms of the obtained results, so for the physiological signals, there's EEG signals, electrical encephalography, skin conductance or governing skin response, and finally the heart rate variability. As measures, we look at how the user turns around. So we always log their turning direction towards the left or towards the right. Whenever they hear the voice telling them to go left or right, to turn left or right, as well as their player of rounds they manage to complete given the amount of time that we allocated to them, which I think is about 7 minutes per session. And then we have also subjective measures, which are questionnaires. We have them fill up the nasal TLX, task load for cognitive load, system trust scale for the perceived trust, and finally the subjective mental effort questionnaire. I'll now move on to the results. So from our study, we found that there was a significant main effect of cognitive load on the alpha band power. So from the EEG signals that we gathered, we only extracted the alpha band power from the related work. We found that there was some significant effects. This analysis of the average alpha band power, there was a 71% decrease in the alpha band power from the low to high cognitive load for the and as well as 27% increase in the alpha band power from low to high cognitive load for the high accuracy voice assistant, which is actually in line with previous work because actually the EEG alpha band power is inversely proportional towards the cognitive load. As for the Gsr signals, we performed the NFT analysis, and we found that the mean and peak frequency significantly differs across different levels of trust. One interesting finding that we found is that there was a significant main effect of cognitive load on the total power of the therapy at approximately 0.05 Hz, as well as 0.12 Hz. So we think this is rather interesting. I think there's been some related work that we cited in the paper, saying that this range has some correlation towards the cognitive load, and we found that 0.05 Hz and 0.12 Hz to be significant. However, when looking at heart rate variability, we did not find any significant main or interaction effects towards the results. By looking at the descriptively low to high frequency ratio, which is a common feature used for heart rate variability analysis, 24% increase in mean from the low to high cognitive load for no voice assistance, 20% increase in the mean from low to high for low accuracy voice assistance, and finally 2% decrease in mean from low to high cognitive load for high accuracy voice assistance. Looking at the behavioral measures, so as in the head movements and the around per second, for the didn't find any significant interaction effects, we did find a decrease of by 4% in high cognitive load compared to low cognitive load between the different voice accuracy levels, as well as an increase by 0.7% in high cognitive load compared to low cognitive load by looking at only the high accuracy of the voice assistance. Looking at the rounds per second, though, we found that towards the accuracy of the voice assistance or the trusting distance or the trusting with the voice assistance. Looking at the subjective measure, so for the system trust scale, so all three questionnaires showed significance, where the system trust scale shows the main effect in accuracy and cognitive load, as well as the interaction between nested test load shows the main effect in accuracy as well as cognitive load, as well as the subjective mental effort questionnaire, which has the main effect towards cognitive load. So I'm going to go through the discussion right now. So we found that overall for the EEG, that the alpha band power was indicative of the user's cognitive load, which was in line with previous related work, because the reduce in alpha band power indicates an increase in physiological cognitive load. For the Gsr Signals, there was a amplitude from total power analysis at 0.05 Hz and 0.12 Hz, which reflects this cognitive loads in relation to different class levels. For heart rate variability, there was a decrease in mean, even though there was no significance, but we do think that this is for future works, as well as means that the LFHF ratio increased even for conditions with no agent. Some interesting feedback that we got from participants is that they feel that the voice assistant helped make the job easier, but they would actually prefer to not have any voice assistance if the helper is inconsistent. So compared to low accuracy voice assistance, it's even better to not have one at all, because it probably just confuses them. A very interesting feedback that we got is that some of them actually take the direction given by the voice assistant as a form of heads up. So even if it's right, because if it's correct, it's great. Otherwise, there's a 50% chance that it's wrong and it just turn the other direction. So